How we doing, guys? Just a short video here on where some of the equations that we work on come from. Today I want to show this one in particular. I'm assuming you've seen chapter 12, differential equations. And we're starting here with our definition of simple harmonic motion, which is that acceleration is proportional to distance and in the opposite direction. Okay, remember omega squared is just some constant. It does relate to angular frequency, as we've seen in other videos. So if you're starting from your mean position and you're oscillating back and forth, at some point in your movement, you're going to reach your full amplitude, and at that point your velocity will be zero. Okay, so we're going to use that as a condition in this in just a second. If I change this into a differential equation, if I can say that the second derivative, well, if I say dv dt is minus omega squared x, and if you remember our old trick, the chain rule, dv dx times dx dt is another way of stating dv dt, and dv dx dt, sorry, can be written as v. dv dx we'll leave as it is another way of saying our acceleration. Okay, so v dv dx equals minus omega squared x is another way of saying acceleration is minus omega squared x. And doing our little separation of our differential, our funny little thing there, we get v dv is equal to minus omega squared x dx. Okay, so we're integrating on this side with respect to x, this side with respect to v to solve that. Remember, omega squared is just some constant, so I'm actually going to bring it outside the integral signs. And we integrate between what limits? Well, our position at some random stage will be x, and our velocity at that point will be v. At a very definite stage here, at the full extent of our motion, our position will be the full amplitude and our velocity will be zero. So we are going to integrate between 0 and v for velocity, and we're going to integrate between a and x for distance, for displacement. So what do we get? V squared over 2 evaluated between 0 and v is equal to minus omega squared times x squared over 2 evaluated between a and x. Well, this is going to give us v squared over 2 minus 0 squared over 2, which is just 0, equals omega squared minus omega squared times x squared over 2 minus a squared over 2. Okay, so ignoring that 0 and then multiplying through by 2, we're going to get v squared equals minus omega squared times x squared minus a squared, which is the same as omega squared times minus omega times a squared is plus a squared, minus omega times minus x squared is minus x squared. Okay, so that's where that one comes from. I'll just briefly talk about our y equals, I'm going to look at cos omega t plus epsilon. I've looked at sine omega t in another video, and why that's a solution to this. Well, if that is our if that's our distance, so I'll call that x for displacement, is cos omega t plus epsilon. Dx dt, our velocity at any point, differentiate that will be, differentiate cos, you get minus sine of the same argument, omega t plus epsilon, all multiplied by, according to the chain rule, the differential of the argument, which is omega. Differential with respect to t, that disappears, it's constant, t to the power 1 just becomes 1, so omega. So that's minus omega sine omega t plus epsilon. Our second differential, which is our acceleration, d2x dt squared, is going to be again minus omega, differentiate sine, you get cos omega t plus epsilon, again multiplied by, according to our chain rule, omega, the differential of the argument, and that is minus omega squared cos omega t plus epsilon, which is what we started with, so that's minus x. So the acceleration is minus omega squared times x, which is our definition of simple harmonic motion. And hopefully you can see there how angular frequency relates to this constant omega squared that I keep talking about. Lastly, just to really emphasize this because we use it a lot, periodic time is 2 pi radians divided by your angular frequency in radians. So the angular frequency tells you how often your cosine is repeating itself. So essentially, if that's 360 degrees and that's 60 degrees per second, to work in degrees, your period would be 6 seconds. It would take 6 seconds to get around. We're working in radians. It's 2 pi radians and some number in radians per second. But that gives us our periodic time as well. Okay, leave it there. See you in the next video.